Okay, I've had a lot of folks asking me how the charger operates, how it actually functions, what it does, etc. So I'm just going to try to describe some of the very simple processes involved in it, and I'll try to just so a few simple circuits here. I'll try to point it back to components that are actually inside the physical circuit. Okay, this charger is essentially a switched mode power supply, and it's based on the principle of a buck converter. And you can do a quick search on the internet and get all of the fancy info that you please on that. But what a buck essentially does is it takes a high voltage, and by switching two parts I can translate that into a low voltage. And if I vary with the PWM signal, the time that I have this switch here on for, I can decide how much power that I send out to this part of the circuit. So for this application, as in a battery charging, it's a quite simple and efficient means of taking a high voltage AC, converting it into DC, feeding it through a buck circuit, and controlling the charge of pretty much any type of battery chemistry. So the first stage in the actual circuit is where we take our 240 volts AC input here, single phase AC, and the first thing inside the charger that we see when we actually go in there is we see the RCBO. Now what that part does, it combines two functions. The first function is a standard 32 amp AC circuit breaker, which is a two poles live neutral. And the second function that it has is that it has a 30 milliamp RCD in it. That's also, I think, called a GFCI circuit. So that prevents the circuit from drawing too much current, and if there's any imbalance in the two currents, it will turn off. So if you had a short circuit going to earth, or if somebody touched a terminal or something, it would turn off the power supply and prevent fires, injuries, shock, all that sort of thing. So that's a very important part to have in your charger circuit, no matter what kind of charger that you actually have, whether it's one that you build or buy, that component should be included in there. So secondly then, our AC comes in here, and we tail off through a little fuse. There's about a half an amp fuse there, and we just go into a little power supply that just takes our 240 volts AC and creates 12 volts DC to drive all the control circuitry contactors, DC-DC converters, control board, all that sort of thing. So that's just a little general purpose off-the-shelf power supply. So our AC current continues here, and it gets to the first contact on our contactor. And going across that contact, we have 100 R, I think it's a 10 watt resistor. Now the purpose of that is to perform a pre-charge function on this DC bus capacitor here, and it prevents a very high current flow that could blow fuses, trip circuit breakers, damage diodes, all that sort of thing, in the event that we simply plugged in here and closed that contact. There would be a huge current spike going through here to charge that capacitor. That's a 1000 UF 400 volt electrolytic cap, so it's quite a big component and it stores a lot of energy. So when the circuit is first plugged into the mains, this contact is left open, so this current flows through this part here, and it typically can only get to about 2.5 amps, and it only takes half a second to charge that bus capacitor, after which time then the current flow through that falls away to 0, and when the charger turns itself on, this contact closes, and that essentially allows power to bypass the resistor and flow straight into the diode bridge. So the final part that we have here is we have a single phase bridge rectifier and a filter capacitor, and the purpose of that is to convert our 240 volts AC into a DC bus across here that's approximately 300 to 320 volts DC. That's with a 240 volts AC input. A question I'm frequently asked about this charger is, could it actually operate on 120 volts AC? The answer to that is it can. The difficulty is that with a 120 volts AC input, typically the DC bus voltage here will only be about 150 to 160 volts DC, and it means that the maximum battery voltage that I could expect to charge from this would be at best a 120 volt system. Now there are other extraordinary possibilities with PFC circuits and boost converters to get around that particular problem, but I gotta be honest, it's not a problem for me here, so I'm going to leave that part of the design to others. So when we get out of our DC bus here, the next part of the circuit that we actually go to is the nitty-gritty of the actual buck converter itself. Now if we go back to our simple theory circuit here, you can see that we have two switches and an inductor. Well, in practice, the top side switch here, SW1, is that function is taken care of by this top side IGBT here, and SW2, this guy, is handled by the body diode of this low side IGBT that has its gate and emitter tied by a short circuit, and the purpose of that is that it allows us to avail of the fact that a commonly available push-pull IGBT block can be employed for this circuit, and it greatly simplifies the setups, connections, all that sort of thing. So our top side IGBT here takes our 300 volts DC, and when it turns on, it conducts that through the inductor, out through the output diode, and out to our battery, which should be set up here between these two terminals. Now that top side IGBT is controlled by a very fast pulse train. It's a PWM system, and by varying the Mark II space between the pulses, I can decide how much of that 320 volt DC bus that I feed out to my battery pack. And when the top side turns off here, the inductor will try to keep the current flowing. That's the purpose of the inductor. It's a bit like a spring, insofar as that when I turn on the power here, I'm going to tension that spring. I'm going to, if you can kind of picture the coils here, when the power comes on, the coils are going to squeeze. I'm going to squeeze them in, and then when I turn off here, they're going to twang back out and keep a current flow going, and the current is going to flow this way through that body diode and back up, and it's got a pathway to flow. As we can see in our theory circuit here, current will flow this way through that diode SW2, and then when I switch back on the high side, the diode turns off and I start the whole cycle over again. Now there are plenty of better descriptions of buck converters and IGBT drive circuits and all kinds of PSpice and MATLAB and theory here and there, but that's just the very basic principles behind how this charger actually operates. Now there are two things then that I have to sense. I have to sense voltage across my battery terminals, and I have to sense current that passes through the charging circuit. Now I'm going to just try to do the power stage today, and if anybody has sufficient interest, I will do a little bit on the current and voltage sensing stages. I don't want to bore everybody to tears, so what I'm going to do is I'm going to pop the cover off the charger here, and I will try to translate what we see on some of these diagrams here into the physical parts that make up the charger. Okay, so at the start of the video I said that the most important part of any charger is to have circuit protection, and we said that we had our RCBO here, which was across our two input terminals, AC input. So that is physically this component here. So we can see we have 32 amps type B, and we'll see down there we have a 30 milliamp trip and 230 volts AC, and this operates by this handle that I push up, and if I had power to the circuit and I pushed this test button, it would actually trip that it would trip out that handle and it would cut power to the circuit. So our power physically comes in through this gland here. It goes straight in. We have N, L and earth on the side there. So we then said that we had our little fuse here for our DC power supply. So that's that little glass fuse in here. F4 it's called there. And we have a pretty much standard off-the-shelf DC power brick in there. I think it's a 4 amp power supply. It's just the kind of commonly found for toys, power tools, that sort of thing. Anyone that can supply a few amps at 12 volts will fit the bill fine. So we then said that we come across our 100 ohm pre-charge and our contact, which we have here as our pre-charge is just encased in a bit of heat shrink. We can see the contact here. It goes across L4 to T4. That's the live coming out of the RCBO. You can see it goes into the contactor, it's out of the contactor, goes all the way over here where it goes into the bridge. So we have our diode bridge here then, and we're going into that. This is it in the center of the heatsink here, just obscured by this capacitor here. Sorry about that, just this capacitor is in the way. But that's our diode bridge, so that's that component there. We then have our DC bus capacitor that I have kind of hidden under a couple of sheets of mylar there just for safety. You see we have our blue and brown cables going to it from the bridge, so that's that component there. And also on our top diagram it's this component here. Pardon me. Now, coming out of the capacitor then, we then go to the IGBT, which we see it has 3 terminals here because it is the 2-pack part that has a top side and a low side joined up inside the case. So we have C1, E1, C2 and E2. If we go down there, we can just possibly see that that is the C1 terminal there. That's the C1 terminal. You see we have a brown cable on that, and that's bringing our DC bus in there to the top of the IGBT. As we can see, hopefully here, we have the bottom side terminals are short-circuited. Sorry if you can't see that too well. I just literally bent the pins together and soldered them just to keep that link as short as physically I could. And then we have the driver board in here, but I'll get into that in the next installment. So that's our IGBT. And the next phase then that we said was we have our inductor. In this case, that's this big guy here. It's got 2 coils on it and a ferrite core because it's a high frequency circuit. It operates at 32 kilohertz, so it needs a ferrite core so that we don't get eddy currents and all kinds of heating and problems. So we come out of our inductor, we go into a small capacitor, which is this guy here. This is an MKP capacitor, which is just there to smooth out any very big pulses, that sort of thing. And finally we go to a diode, which is this part here, which is this big guy here. This is a big diode. It's far too big actually for this job. It's a 300 amp dual pack diode actually, but I just happen to have it, so why not put it in there. and so far the past 12 months it hasn't had any trouble at all. So we then have our voltage sense circuit, which is on the back here. That's it there. And our current sensing circuit, which is this little guy here, which is this blue this little blue guy here in the middle. It's our current sensor. Just trying to balance this top here. It's a bit top heavy. Here we go. So that is the basics of what we actually have inside the box. Oh yes, just one final thing. There's a choke here. This is a wire hound choke that I fitted to the circuit, and that's it here. As you can see, it looks like a big transformer, but it's just got a single coil on it, and it just basically helps to smooth out the current flow and prevents any fast transients from getting in and causing damage in the battery pack, etc. And so that's about it for the power circuit, folks. Hope I haven't bored everybody to death. But as I say, I've been asked a lot of questions about it. So as you can see, it's quite a simple system. I don't claim that it's perfect. It's got all kinds of flaws and stuff, but if you just want a simple switch mode charger for your car, you can't get better than this, in my opinion anyway. Okay, that's it for now.